Hello guys, today I'm finally thrilled to present you the complete compilation for Geometry Galore after realizing I never did it even though I ended it almost 3 months ago. Hi, I'm FormulaFocus, the founder of this STEM competition Axion Challenge. This is day 1 of Geometry Galore, where I make boring geometry formulas fun. So imagine we have this triangle here. This is the base, this is the height. We can then split it like this. Now, if we draw this imaginary rectangle here, because the dimensions as shown are equal, that means that the triangle is actually half of each rectangle's area. If we think about it, that means the triangle's combined area is half of the rectangle's combined area. Now, if we want to be more rigorous about it, we can assume that A is the length as shown, and then the other length is B minus A. That means that by what we just said, the areas of the two triangles are AH divided by 2 and B minus AH divided by 2 respectively. Now, adding these together to get the area of the combined triangles, we can then factor it as so, giving us BH divided by 2. We have just proven the formula for the area of a triangle. This is day 2 of Geometry Galore, where I make boring geometry formulas fun. Today we're talking about the 5 ways to calculate the area of a triangle. The first one is normal, where if we have a triangle and we know its base and height, its area would be base times height divided by 2. The next one is Heron's formula, which would only be used if you know all the sides of a triangle. If the sides of the triangle are A, B, and C, the area would be S times S minus A times S minus B times S minus C, where S is A plus B plus C divided by 2, often called the semi-perimeter, because it's the perimeter of the triangle divided by 2. So for example, if we had a triangle with sides 3, 4, and 5, obviously this is a right triangle, but we can use Heron's formula too. S would be 6, and we can plug into the formula to get square root 6 times 3 times 2, which would equal to 6. Just like if we were to use a base times height formula. Now next we have the in radius, where if we have a circle inscribed in a triangle and its radius is r, the area would be r times s, where s again is a semi-perimeter like last time. So for example, if we had a triangle with a circle inscribed in it with the in radius of 3 and all the sides of the triangle are 4, s would be 6, and then as said the in radius is 3, so then we can multiply these together to get 18. The fourth way to find the area would be using the circumradius, which is kind of the opposite of the last one. And so this would be if we have a triangle inscribed in a circle, and if the sides of the triangle are A, B, and C, the radius of the circle is r. The area of the triangle would be ABC divided by 4r. So for example, if we have a triangle inscribed in a circle with sides 3, 4, and 5, and the radius of the circle is 3, the area of the triangle would be 3 times 4 times 5 divided by 4 times 3, which would cancel out to get 5. The fifth and final way would be using trigonometry, which kind of sucks. So if we had a triangle with sides A, B, and C, where angle C is opposite of side C, the area of the triangle would be half AB sine C. So for example, if we had a triangle with sides 3, 4, and 5, as said, this is a right triangle, but we can also use this formula as well. The area of the triangle would be half AB, which would be 3 times 4 times sine angle C, which is 90 degrees, and then multiplying this would get 6, which is the same as if we were to use base times height. This is day 3 of Geometry Galore, where I make boring geometry formulas fun. Today we're talking about similar triangles. So similar triangles are when two triangles are proportional. There are 5 types of similarity or ways to prove that two triangles are similar. AA, SAS, SSS, HL, and LL. AA similarity stands for angle-angle, and it's when two angles of two triangles are the same. This is the most common type of similarity, and it's AA, not AAA, because the triangle's angles always sum to 180 degrees, so if two angles of two triangles are the same, the last two would be the same as well. This type of similarity is also most seen with parallel lines and lots of right angles in a figure. The next type of similarity is SAS, which stands for side angle side, and it's when two sides of two triangles are proportional, not the same, and the angle in between these sides are the same. It is important to note that the angle must be in between these two sides, as SSA is not a type of similarity. So for example, if we had two right triangles, one with legs 3 and 4 and one with legs 9 and 12, since their legs are proportional with a scale factor of 3, and we know that the angle in between their legs are 90 degrees, these two triangles are similar. The next type of similarity is SSS, or sides to side, and it's when all three sides of two triangles are proportional. So for example, a 3, 4, 5 and a 9, 12, 15 triangle are similar. These next types of similarity are right triangle only. The first type of similarity that applies to right triangles only is HL, or hypotenuse-like, and it's when in two right triangles the ratios of their hypotenuses and one of their legs is equal. So for example, with two right triangles, one with a hypotenuse of 5 and a leg of 3, and another with a hypotenuse of 15 and a leg of 9 are similar because their ratios of hypotenuses and legs are 1/3. Last type of similarity is LL, or leg-leg, and it is when in two right triangles the two ratios of the triangles' legs are equal. It is important to note though that this is technically an example of SAS similarity, since we know that the angles in between both of the triangles' pairs of legs are 90 degrees. An example of LL similarity is with one triangle with the legs of 3 and 4 and another one with the legs of 9 and 12, since the ratios of their legs are 4/3. Warning, as I said earlier in the video, SSA is not a type of similarity. To have two triangles be similar, the angle must be in between the two legs. This is day 4 of Geometry Galore, where I make boring geometry formulas fun. Today we're looking at a problem utilizing similar triangles. I personally found this problem pretty interesting.
Oh my god, bro. Oh, hell no, man.
When I first did it. It reads, let ABC be a scaling triangle. Point P lies on BC, so that AP bisects BAC. The line through B perpendicular to AP intersects the line through A parallel to BC at point D. Suppose BP equals to 2 and PC equals to 3. What is AD? So this was a diagram shown in the solution, and we can assume X and Y are the points as shown. Then since BY is a straight line, angle AXY is a right angle. Then since triangles AXY and ABX have two pairs of equal angles, the last pair of equal angles would be equal as well. So then they're similar. But in fact, since they share one common side, they're actually congruent. This then means that their hypotenuses are equal. Angle bisectors can remind us of the angle bisector theorem, where if we have a triangle ABC where BD is an angle bisector, AB divided by AD equals to BC divided by CD. Plugging this into the angle bisector AP, we get that AB divided by AC equals to 2/3. Then, since AB and AY are equal, if AB is 2x and AY is also 2x and YC is x. We then know that angles AYD and BYC are equal. We still haven't used the fact that AD and BC are parallel. We can then draw the red Z as shown. This will show that angles DAC and BCA are equal. Since triangles ADX and BCX have two pairs of equal angles, they are similar. This means that the ratio of a pair of sides, one side from each triangle, equals to the ratio of another pair of sides, as long as the angle opposite of both sides in the ratio are equal. That kind of sounds wordy, but that means that the ratio of side YC to AY is equal to the ratio of side BC to AD, since the angle opposite of sides YC and AY are equal, and the angles opposite of side BC and AD are equal as well. The ratio of side YC to AY is 1:2, which we saw earlier. This means that the ratio of side BC to AD is also 1:2 as well. Since we know that BC equals to 5, you can get that AD equals to 10. This is day 5 of Geometry Galore, where I make boring geometry formulas fun. Today we're talking about special triangles. The first type of special triangle is a 30, 60, 90 triangle, where if we have a triangle with angles 30 degrees, 60 degrees, and 90 degrees, its ratio of sides would be 1, square root 3, and 2. It is important to note that the side opposite to the 30-degree angle must be the shortest side, or in other words have the length of 1 in terms of the ratio. The side opposite to the 60-degree angle must be the second shortest, and the side opposite to the 90-degree angle must be the longest. This is because the larger the angle opposite to the side is, the longer the side will be. An example of a 30, 60, 90 triangle is a triangle with two legs of 2 and 2 square root 3 and a hypotenuse of 4. The next type of special triangle is a 45, 45, 90 triangle, and it's basically an isosceles right triangle. Its lengths are in a ratio of 1, 1, square root 2. We can prove this because if we have a right triangle with two legs of x, by the Pythagorean theorem, the hypotenuse would be square root x squared plus x squared, which is square root 2x squared. which can then be factored out into x times square root 2. An example of a 45, 45, 90 triangle is a triangle with two legs of square root 2 and a hypotenuse of 2. The last type of special triangle is an equilateral triangle, where all of its sides are equal. Since all of its sides are equal, its angles are also equal as well, being 60 degrees. If a side of the equilateral triangle is a, the area would be square root 3 divided by 4 times a squared. This could be proved by drawing a height down the middle of the equilateral triangle, which would create two 30, 60, 90 triangles. So for example, if we have an equilateral triangle and all of its sides are 3, its area would be square root 3 divided by 4 times 3 squared, which is 9 square root 3 divided by 4. This is day 6 of Geometry Galore, where I make boring geometry formulas fun. In this problem, we know that the area of the whole figure is 183 feet squared, and it's asking us what h is. We can immediately notice that the figure is two 45, 45, 90 triangles overlapped together. Looking at the bottom left of the figure, we can see that the whole angle is a right angle, and so the angle as shown is 45 degrees. Then since the angle in the top left is a right angle, the triangle outside of the figure is a 45, 45, 90 triangle as shown. From the ratio of a 45, 45, 90 triangle, we know that one of its legs is 8, and so its hypotenuse is 8 times square root 2. That means that the area of the triangle in the figure is 8 times square root 2 squared divided by 2, which is 64. Doing the same for the right side of the figure, we can see that the triangle outside of the figure is a 45, 45, 90 triangle, meaning that its hypotenuse is 12 times square root 2. Same as last time, the area of the 45, 45, 90 triangle with legs of 12 square root 2 is 12 square root 2 squared divided by 2, which is 144. However, adding these two areas together would give us 208, which is already more than 183. The reason why this is because if we look at the figure as the red, green, and yellow regions as shown, the first triangle's area is the red and green region combined, and the second triangle's area is the yellow and green region combined. We can notice that we counted the green region twice, so we need to find its area to subtract it. Looking at the red triangle, since one of its angles is 90 degrees and its other angle is 45 degrees, the last angle would be also 45 degrees. Same thing for the yellow triangle, its last angle will also be 45 degrees. Since h is the height, we know that it creates a right angle, and so the angle as shown is 45 degrees. If we know that one of the triangle's legs of a 45, 45, 90 degree triangle is h, its other leg would be h as well. Two of these 45, 45, 90 triangles would create a base of 2h, and since the height is h as said, the area of the triangle would be 2h times h divided by 2, which is h squared. Subtracting this from the total area that we got earlier, which we overcounted by, we would get the actual area of the figure, which is 183 square feet. Solving this equation, we would get that h equals to 5. This is day 7, cough cough, of Geometry Galore, where I make boring geometry formulas fun. Today we're speedrunning quadrilaterals. The first quadrilateral is a square where all of its angles are right angles and all of its sides are equal. If its side length is s, then its perimeter is 4s and its area is s squared. Then we have the rectangle, very similar to the square, where all of its angles are right angles, but it has two pairs of equal sides instead of all of its sides being equal. Its area is BH, where B is the base and H is the height, and its perimeter is 2B plus 2H. An interesting property of the rectangle is the British flag theorem, where if we have rectangle ABCD where P is a random point in the rectangle, PA squared plus PC squared equals to PB squared plus PD squared. Then we have the rhombus with two pairs of parallel sides and all of its sides are equal. If it has the diagonals of D1 and D2, its area is half D1, D2. This can be proven because the rhombus is composed of 4 right triangles. Then the rhombus's perimeter is 2 times square root d1 squared plus d2 squared, which can be proved by the Pythagorean theorem. Second to last, we have the parallelogram with two pairs of parallel sides. If it has a base and height as shown, its area is BH. This can be proven because drawing the height, the red line, as shown, we can move the resulting right triangle to the right, which would create a rectangle. And last but not least, we have the trapezoid, which has one pair of parallel sides. If it has bases B1 and B2 as shown, its area would be B1 plus B2 divided by 2 times h, where the first part is the average of the bases and h is the height. This is day 8 of Geometry Galore, where I make boring geometry formulas fun. Today we're looking at the basics of circles. So imagine we have a circle with its radii coming out, creating an angle. If this angle is theta, what is the area of the circular sector? So we know that the area of the total circle is pi r squared. Thinking about the circular sector in terms of a pi, we know that each degree is 1 over 360 of the circle. So theta of those would be theta over 360. This means that the area of the circular sector would be theta over 360 times pi r squared. Same thing with circumference. The total circumference is 2 pi r, and so the circumference of the circular sector is theta over 360 times 2 pi r. Next, if we have a similar setup where the center of the circle is O and radii are coming out, if the length of the arc as shown is theta, what is the angle as shown? If you said theta, you would be correct, and this is true for all angles, meaning that the length of the arc is equal to the angle as shown. It is important to note that the point O as shown must be the center. However, there is another case. If we have two chords creating an angle as shown, and the length of the arc as shown is theta, what is the angle? If you said theta divided by 2, you would be correct. Again, this is true for all angles, and so the angle as shown is equal to the length of its arc divided by 2. And this is known as the inscribed angle theorem, which is extremely important. And finally, if we have a right triangle inscribed in a circle, its hypotenuse would be the diameter. We know this is true because as shown, we can draw different variations of a right triangle and they would all have the same hypotenuse. And this also works in reverse, so if the hypotenuse of a triangle is the diameter of the circle, the triangle is a right triangle. This is day 9 of Geometry Galore, where I make boring geometry formulas fun. In this problem, we know that the area of the semicircle with diameter AB is 8 pi, and the length of the arc of the semicircle with diameter AC is 8.5 pi. The problem is then asking what the radius of the semicircle with diameter BC is. Since we know that the area of the semicircle as shown is 8 pi, we know that pi r squared divided by 2 is 8 pi, and so r is 4. This then means that the side of the right triangle as shown has a length of 8. Then since we know that the length of the red arc is 8.5 pi, we know that 2 pi r divided by 2 is 8.5 pi, and so r is 8.5. This then means that the side as shown is 17 because it's the diameter. To find BC, we can do the Pythagorean theorem on triangle ABC, which would give us that BC is 15. And since the radius of the semicircle with diameter BC is half of the diameter, which is 15, we know that R is 7.5. Wait, take a look at this formula. Isn't it so cool how the angles outside of the circle shapes the arcs on the circle? This is day 11 of Geometry Galore, where I make boring geometry formulas fun. Today we're talking about advanced circle properties, which can get really weird. The first one is tangency and right angle, which is pretty common, which states that if we have a radius coming out of a circle as shown with the line tangent to the circle and line, there would be a right angle as shown. Now here is where it gets really weird, because the next ones are so uncommon that I don't even have a name for them. The second formula, with no name, says that if we have a circle as shown with an angle outside drawn, angle APC equals to arc BD minus AC divided by 2. If we then color code it, it would result as so. Next, another no name. If we have a circle as shown with a cross going through it and points as shown, angle BPC equals to APD, which equals to arc BC plus AD divided by 2, aka the average of the arcs. Again, we can color code it as so. And finally, the last no name. I think that this one is the weirdest one of them all because I don't really use this one very often. If we have a tangent r as shown, angle RQP equals to half the arc angle. The angle would be if we technically drew these two radii as shown with center O. However, I don't really think that that's necessary, as we can just refer to it as the arc angle. Now remember, except for the first one, all of these properties are kind of uncommon. So if you're a beginner, I would recommend going to my last video and coming back later to learn more about circles. Everyone tells you to use pop, but no one ever tells you how to use it. Wait, were you thinking of soda? No, I'm talking about power of a point. This is day 12 of Geometry Galore, where I make boring geometry formulas fun. As said in the intro, we're talking about power of a point, which measures a point's relative distance to a circle. Now, the reason I think that this theorem is called power of a point is because whatever point that the theorem is talking about has literally all the power on the theorem. So for example, if we have power of a point with two tangents where P is a external, and there are two tangents tangent to the circle as shown, these two tangents would be equal. So I was actually originally going to do 5 theorems, but then I realized that I could condense into 3, so I'm going to save a lot of your time. You're welcome. Anyways, these theorems are getting so weird because more and more of them are starting to have no names. But anyway, this one states that if we have 2 seconds, as shown, PA times PB equals to PC times PD, which equals to R squared minus OP squared. And finally, we have another no name where if we have a setup as shown, where seconds AB and CD intersect P as shown, PA times PB equals to PC times PD, which equals to OP squared minus R squared, where R is the radius of the circle. I also forgot to mention this here, but we can also have a tangent PT as shown, where its square equals to PA times PB, which equals to PC times PD too. Do you know who this guy is? Well, if you don't, keep watching. This is day 13 of Geometry Galore, where I make boring geometry formulas fun. Today we have a problem that says a triangle has sides of length 2, 5, and 6. A Sevian drawn to the longest side divides that side into segments in a 2-to-1 ratio. Compute all possible lengths of this Sevian. So if the longest side, 6, is divided into 2-to-1 ratio, that means that it would be divided into 4 and 2. Then, drawing a diagram, we notice that we have 2 possibilities. The 4 is on the right or the 4 is on the left. However, there is simply no way we can find the length of this Sevian, right? We don't know any angles or anything about this. Well, let me introduce you to Stewart's theorem. If you would like to know, this theorem is named after a mathematician named Matthew Stewart who published the theorem in 1746. So anyways, this theorem says that if we have a triangle with a Sevian going through it as shown, with lengths as shown, MAN plus DAD equals to BNB plus CNC. Now a fun way to remember this is a man plus his dad put a bomb in a sink. Don't ask me. Yeah, no. Now using this theorem on the first figure, we get 4 times 6 times 2 plus D times 6 times D equals to 2 times 4 times 2 plus 5 times 2 times 5, which would give us that D equals the square root 3. Then for the second figure, we get that 2 times 6 times 4 plus D times 6 times D equals to 2 times 2 times 2 plus 5 times 4 times 5, meaning that D equals the square root of 10, giving us our 2 answers. You know how Google Maps is able to find the shortest distance for your route in under 2 seconds? Well, it goes back to something called analytical geometry, which sounds scary, but isn't. This is day 14 of Geometry Galore, where I make boring geometry formulas fun. Today we have a problem that says 2 points are 10 units apart. The slope of the line between them is 3. One point is 2, 1. Find the second point in the equation of the line. So we know that one point is 2, 1, and so we can treat the other point as xy. Now we know that these 2 points are 10 units apart, but how do we express that distance? Well, thinking about it, if we have 2 points on the coordinate grid as shown, it creates a right triangle. Now this right triangle has legs of x minus 2 and y minus 1, no matter where xy is. So for the overall distance, which is the hypotenuse, we can express it using the Pythagorean theorem, and we know that this is 10. Expressing the distance between 2 points as shown is known as the distance formula. Next, we know that the slope of the line between 2, 1 and xy is 3. So this means that the line passes through 2, 1 and xy, of course. We can write the equation of a line on the coordinate grid as y equals to mx plus b, where m is the slope and b is a y-intercept, which is where the line intercepts the y-axis. So x-intercepts would be where the line intersects the x-axis. Anyway, since we know that the line passing through these 2 points is 3, we know that m is 3, and so we can write the equation of the line as y equals to 3x plus b. Plugging 2, 1 into that would get that b equals to negative 5, meaning that our equation of the line is y equals to 3x minus 5. But we still need to find the second point, so how do we find that? Well, we still haven't used the fact that the distance between the 2 points is 10, but we have 2 variables. However, we know that y equals to 3x minus 5 from what we had just got, and so plugging that in, we'd had to use a quadratic formula because this quadratic is not very easy to factor. And we get that x equals to 2 plus minus square root 10. If x equals to 2 plus square root 10, y would equal to 6 plus 3 square root 10 minus 5, which is 1 plus 3 square root 10. Then if x equals to 2 minus square root 10, then we get that y equals to 1 minus 3 square root 10. This means that we actually have two options of what our point can be. 2 plus square root 10, 1 plus 3 square root 10, and 2 minus square root 10, 1 minus 3 square root 10. Ever wonder how architects know exactly how much to tilt a building to catch the most sun? It's all about trigonometry. This is day 15 of Geometry Galore, where I make boring geometry formulas fun. Today, we're going to be going over a trigonometry lesson together. So imagine we have a right triangle with the hypotenuse as shown. Now let's look specifically at this angle. The leg closer to the angle would be adjacent to the angle, and the leg further away would be opposite. So our first trigonometry function is called sine, which would be abbreviated to sin, or sin. And it's basically a fancy way of saying the opposite side of the triangle divided by the hypotenuse. Then there is cosine, which can be abbreviated to cos or cos, which is the adjacent side divided by the hypotenuse. Then there is tangent, abbreviated to tan, which I would like to think as the kind of baby of sine and cosine, since it's the opposite divided by the adjacent side, aka sine divided by cosine actually. These are the most common types of trigonometry functions, so I recommend memorizing these before going on to the other ones. Like cosecant, which is abbreviated to CSC, and it's the hypotenuse divided by the opposite side, which is also 1 over sine A. Then there's secant, abbreviated to SEC, and it's the hypotenuse divided by the adjacent, aka 1 over cosine. I find it kind of ironic that cosecant is 1 over sine A when it starts with C, and secant is 1 over cosine A when it starts with S. Anyway, so next we have cotangent, which is COT, and it's the adjacent divided by the opposite, aka 1 over tan A, which is really easy to remember. Anyway, side note, a really easy way to remember sine, cosine, and tangent is through the abbreviation SOHCAHTOA, where SO is for sine, CA is for cosine, and TOA is for tangent. Anyway, it's quiz time! If we have a 30, 60, 90 triangle, what is sine 30 degrees? Since the ratio of a 30, 60, 90 triangle is 1 square root 3, 2, and sine is the opposite side divided by the hypotenuse, our answer would be half. Now, if we have a 45, 45, 90 triangle, what about cosine 45 degrees? The ratio of a 45, 45, 90 triangle is square root 2, square root 2, 2, and since cosine is adjacent divided by hypotenuse, our answer would be square root 2 divided by 2. Now notice how both of these examples relied on ratios from triangles that we already know. But what about funky angles like 15 degrees, for example? Well, that's what we'll go over in the next video. Sailors have been using angles for centuries to find their way. Turns out the unit circle is our secret weapon. This is day 16 of Geometry Galore, where I make boring geometry formulas fun. Today we're figuring out how trigonometry works on the unit circle. Remember the figure above? Well, let's put that triangle into the unit circle. If we have a 30, 60, 90 triangle as shown, see that from the ratio of the sides, sine 30 degrees would equal to half as normal. However, you know how I said that we're looking at the unit circle? Well, the hypotenuse is actually the radius of the circle, and so it should be 1 instead of 2. Then we need to still follow the ratio, and so the legs 1 and square root 3 must also be divided by 2 as well. But what about angles that extend beyond the first quadrant, like cosine of 120 degrees? You might think that we can just draw a 30, 60, 90 triangle as shown again, meaning that cosine 120 degrees equals to half. However, this is actually wrong. The leg with length 1 is actually going in the negative direction, meaning that it would be length -1 instead of +1. Then the hypotenuse is always positive, and the leg with length square root 3 is going in the positive direction, so cosine 120 degrees equals to -half. And also, since legs in different quadrants are always going in the positive or negative direction, all trigonometric functions have the same sign in different quadrants. Now let's try another example. If we have a 45, 45, 90 triangle in quadrant 4, For the angle, 3 of the quadrants sum up to 270 degrees, and then the last one has an extra 45 degrees, resulting in 315 degrees. However, it can also be just 360 minus 45. And the original ratio is square root 2 square root 2, 2. However, it would then be square root 2 divided by 2 square root 2 divided by 2, 1, because the hypotenuse is the radius and it equals to 1. Then the leg going down would be changed to negative since it's going into the negative y direction. So if we were to find something like cosecant 315 degrees, it would be 2 divided by negative square root 2, which equals to negative square root 2. Oh, and you know what time it is. It's quiz time. If we have a unit circle on the coordinate axis and a 45, 45, 90 triangle in the third quadrant, cot what angle equals to what? Well, first we can find the angle, and since the first two quadrants sum up to 180 degrees plus another 45, that would be 225 degrees. Then, since the ratio of a 45, 45, 90 triangle is square root 2 divided by 2, square root 2 divided by 2, 1, but the leg going down is negative, cot 225 degrees equals to negative 1. So where do you see trig in your everyday life? You're about to nail your friend with the water balloon, but you need to know the exact angle to throw it to make sure it lands perfectly. With a few measurements, the law of sines and cosines can help you do this. This is day 17 of Geometry Galore, where I make boring geometry formulas fun. Today we're going over the laws of sines and cosines. Imagine we have triangle ABC here. We know angle A is 40 degrees, side B is 8, and side C is 12. We are trying to find side A and angle B. What do? To find side A, we can use the law of cosines, which states that if we have triangle ABC where the angles correspond to their vertices and their sides correspond to the opposite side of the angle, a squared equals to b squared plus c squared minus 2bc times cosine A. So plugging this in would get that a squared equals to 8 squared plus 12 squared minus 2 times 8 times 12 times cosine 40 degrees, and using a calculator for cosine 40 degrees would get that a is around 7.81. Now to find angle B, we can use the law of sines, which states that if we have a triangle ABC, which is the same as last time, sine B divided by B equals to sine A divided by A, which equals to sine C divided by C, or you can also flip all of those fractions around. Then plugging this in would get that sine 40 divided by 7.81 equals to sine B divided by 8, meaning that sine B is around 0.6584 and B is around 41.18 degrees. Optionally, we can find that angle C is 98.92 degrees. So what other real-world problems can you solve with this? Let me know below. Ever wonder how game developers make sure your sniper shot lands exactly where you aim, even with bullet drop and target movement? The secret is sum and difference identities. And no, I'm not talking about addition and subtraction, I'm talking about trigonometry. Day 18 of Geometry Galore, where I make boring geometry formulas fun. Today we're figuring out the trig of funky angles with sum and difference identities. For both the sum and difference identities, we have sine, cosine, and tangent. So for sine, we have sine alpha plus beta, which is not the same thing as sine alpha plus sine beta, by the way, equals to sine alpha times cosine beta plus sine beta times cosine alpha. Then we have cosine alpha plus beta, which equals to cosine alpha times cosine beta minus sine alpha times sine beta. Then for tan, we have tan alpha plus beta equals to tan alpha plus tan beta divided by 1 minus tan alpha tan beta. And for the angle difference identities, once again we have sine, cosine, and tangent, and for sine we have sine alpha minus beta, which again is not the same thing as sine alpha minus sine beta, equals to sine alpha cosine beta minus sine beta cosine alpha. And for cosine, we have cosine alpha minus beta equals to cosine alpha times cosine beta plus sine alpha times sine beta. And finally for tan, we have tan alpha minus beta equals to tan alpha minus tan beta divided by 1 plus tan alpha tan beta. Now I have some bad news for y'all. There is no way to memorize these identities in an easy way, at least in my opinion. But I think the easiest way to do this is to repeat examples. So for example, what is tan 15 degrees? Well, we can use a tan subtraction identity, where tan alpha minus beta equals to tan alpha minus tan beta divided by 1 plus tan alpha tan beta, where alpha is 45 degrees and beta is 30 degrees. Now I'll just give this to you. Tan 45 degrees is 1 and tan 30 degrees is 1 over square root 3 or square root 3 divided by 3. And so plugging this in and simplifying, we get that tan 15 degrees equals to 3 minus square root 3 divided by 3 plus square root 3, which simplifies to 2 minus square root 3. So in the comments, can you tell me what something like cosine 75 degrees would equal? I'll tell you the answer in the next video. You practice your free throws constantly, but some days you just can't sink them. What's going on? Well, the trick double angle and half angle identities explains. This is day 19 of Geometry Galore, where I make boring geometry formulas fun. Before we go into the very exciting double and half angle identities, we first need to go over what cosine 75 degrees equals to. We can use a sum identity for cosine, which states that cosine alpha plus beta equals to cosine alpha cosine beta minus sine alpha sine beta, and we can set alpha to 45 degrees and beta to 30 degrees. Plugging this in and plugging in the values would get square root 2 divided by 2 times square root 3 divided by 2 minus square root 2 divided by 2 times half, which simplifies to square root 6 minus square root 2 divided by 4. So first of all, for double angle identities, we have sine, cosine, and tangent like last time. So first of all, for sine, we have sine 2x, which is not the same thing as 2 sine x, by the way, equals to 2 sine x cosine x. Then we have cosine 2x equals to cosine squared x minus sine squared x, or 2 cosine squared x minus 1, or 1 minus 2 sine squared x. And for tan, we have tan 2x equals to 2 tan x divided by 1 minus tan squared x. For the half angle identities, once again we have sine, cosine, and tangent. And we have sine theta divided by 2 equals to square root 1 minus cosine theta divided by 2, and cosine theta divided by 2 equals to square root 1 plus cosine theta divided by 2, and tan theta divided by 2 equals to sine theta divided by 1 plus cosine theta, which equals to 1 minus cosine theta divided by sine theta. And it's also important to note that sine theta divided by 2 does not equal to half sine theta. So now we can do some examples. We can start with an easy one, sine 60, and we know from the unit circle that it equals to square root 3 divided by 2. However, we can also use the sine double angle identity, which states that sine 2x equals to 2 sine x cosine x, where x equals to 30, and plugging this in we get the same answer. But now some harder ones. For example, what is cosine 15 degrees? We know from the last video that we can use the sum and difference identities. However, I don't think this is the most efficient way. Instead, we can use the half angle identities, which is much easier. As a reminder, the cosine half angle identity states that cosine theta divided by 2 equals to square root 1 plus cosine theta divided by 2. Plugging this in where theta equals to 30 degrees, we get square root 1 plus square root 3 divided by 2 divided by 2. Simplifying this, we'll get square root 6 plus square root 2 divided by 4. So follow for more ways math makes you better at sports. Ever notice how explosions in games look so natural, like they follow real-world physics? There's a core math identity behind that. This is day 20 of Geometry Galore, where I make boring geometry formulas fun. This AMC 12 problem says, suppose sine A plus sine B equals the square root of 5/3, and cosine A plus cosine B equals to 1. What is cosine A minus B? This may sound weird, but trust the process. We can first square both equations and add them together. This will give us sine squared A plus sine squared B plus 2 sine A sine B plus cosine squared A plus cosine squared B plus 2 cosine A cosine B equals to 1 plus 5/3 or 8/3. Now this is where the trig Pythagorean identities come in. There are a couple of them, namely sine squared x plus cosine squared x equals to 1, and 1 plus cotan squared x equals to cosecant squared x, and tan squared x plus 1 equals to secant squared x. However, for this problem, we're going to use the first one, which is also the most common, although second place goes to the third one, with tan in second. Anyway, so back to what we originally got. Notice anything? It contains sine squared A plus cosine squared A, and sine squared B plus cosine squared B, which according to the identity equals to 2. And plugging this in, we get 2 plus 2 sine A sine B plus 2 cosine A cosine B. Minusing 2 would get all of that equals to 2/3. And factoring 2 on the equation, we get 2 sine A sine B plus cosine A cosine B equals to 2/3. But notice anything about the things in the parentheses? It's the same as the cosine difference identity. So using that, we can make the things in the parentheses cosine A minus B, which equals to 1/3. Our answer is B. Imagine two different radio signals trying to talk at once. How do you make sense of that? The trig product to sum and sum to product identities help. This is day 21 of Geometry Galore, where I make boring geometry formulas fun. For sum to product and product to sum, there is only sine and cosine. Starting with product to sum, we have sine, which is sine alpha times sine beta equals a half cosine alpha minus beta minus cosine alpha plus beta. As the name suggests, it turns the product of sine and sine into a sum of cosine and cosine. Speaking of cosine, for cosine we have cosine alpha times cosine beta equals a half cosine alpha plus beta plus cosine alpha minus beta. And finally, for sine and cosine, we have sine alpha times cosine beta equals a half sine alpha plus beta plus sine alpha minus beta. Please note that the half applies to both the cosines or both the sines depending on which identity it is, and not just the first one. Then for sum to product is the same thing. We only have sine and cosine. Actually, technically when it says sum in the name, it actually means both sum and difference because there's both addition and subtraction in here. And so this results in 4 identities in total. The first one is with both cosine and addition, and it says cosine x plus cosine y equals to 2 cosine x plus y divided by 2 times cosine x minus y divided by 2. Then the second one says cosine x minus cosine y equals a negative 2 sine x plus y divided by 2 times sine x minus y divided by 2. And for sine addition, we have sine x plus sine y equals a 2 sine x plus y divided by 2 times cosine x minus y divided by 2. Then finally, for sine and subtraction, we have sine x minus sine y equals a 2 sine x minus y divided by 2 times cosine x plus y divided by 2. Now I think it's a good time for a quiz. Now the first question is, what is sine 135 degrees times sine 75 degrees? Now using your knowledge of the prior video, you probably could have figured out what sine 75 degrees was using the addition identities. However, a more efficient way to do this is with our knowledge from this video. Now the identity we can use is sine alpha times sine beta equals to half cosine alpha minus beta minus cosine alpha plus beta. Now plugging this in, we get half cosine 135 minus 75 minus cosine 135 plus 75, which is cosine 60 degrees minus cosine 210 degrees, which is half times half minus negative square root 3 divided by 2. And so we get 1 plus square root 3 divided by 4. So can you tell me what cosine 75 degrees minus cosine 15 degrees is? I'll tell you in the next one. You know, in most of my hooks, I say the commonly misconcepted thing is not what I'm talking about, but when I'm talking about the trig, quotient, and reciprocal identities, I kind of am talking about quotients and reciprocals. This is day 22 of Geometry Galore, where I make boring geometry formulas fun. Can you believe it's the last day of Geometry Galore? That's actually crazy to say out loud. Anyway, so if you didn't know, last video I said I'd answer this question, cosine 75 degrees minus cosine 15 degrees, and we can use the cosine difference identities, which says cosine x minus cosine y equals a negative 2 sine x plus y divided by 2 times sine x minus y divided by 2. And plugging this in, we get negative 2 sine 90 divided by 2 times sine 60 divided by 2, which is negative 2 times sine 45 times sine 30, which ends up being negative square root 2 divided by 2. Anyways, back to the original topic of the video, which is the quotient identities and reciprocal identities. We can start with the quotient identities. There are only 2 of these. One of these you should actually know, which is tan theta equals to sine theta divided by cosine theta, and the other one being cotan theta equals to cosine theta divided by sine theta. Then onto the reciprocal identities, we have cosecant theta equals to 1 over sine theta, secant equals to 1 over cosine theta, and cotan equals to 1 over tan theta. The cotan one is really easy to remember because cotan and tan, but I also think I've said this in another video. I think it's kind of ironic how cosecant equals to 1 over sine theta and secant equals to 1 over cosine theta when their starting letters are different. But anyway, how do we know these identities are actually true? Well, we can imagine that we have a right triangle with an angle, and the side opposite to this angle can be called O, and the one adjacent can be called A, and the hypotenuse can be called H. Now we can look at the first identity, tan equals a sine over cosine. Tan is opposite over hypotenuse, sine is opposite over hypotenuse, and cosine is A over H. So then the 2 hypotenuses cancel out to get O over A. And it's the same thing for the second identity. Cotan is A over O, cosine is A over H, and sine is O over H. So then the 2 H's cancel out. And it's similar for the reciprocal identities. Cosecant is H over O, and cosine is O over H, so then it's the same. Then second is h over a, and cosine is a over h, and cotan is a over o, and tan is o over a. Now let's try some examples with what we've learned. Let's simplify sec x minus tan x times sine x. We know that sec x equals to 1 over cosine x, and tan is sine over cosine. Then simplifying this and getting it to a common denominator, we get 1 minus sine squared x divided by cosine x. Then the numerators look like the Pythagorean identities, and so using that would get cosine squared x divided by cosine, which is cosine x.